Hello everyone, and welcome back. Today we're going to continue our exploration of linear algebra, and in particular eigenvalues and eigenvectors, and focus on the applications of eigenvalues and eigenvectors to ordinary differential equations. So let's start off by talking a few basics about eigenvalues and eigenvectors, just in case you forgot. So let's assume we have the equation ax is equal to lambda x, and let's assume x is a vector in Rn that is associated to this particular equation, where A is an n by n matrix and lambda is a scalar. So we know that A, if it is a matrix, regardless if it's a numerical matrix or a derivative or anything like that, should be a homomorphism from, and let's assume that it is a numerical matrix, and if that is the case, then it's going to be a homomorphism from Rn to Rn. So if it is a homomorphism from Rn to Rn, that implies that this vector here, x, is also going to be an element of Rm, and that implies that this vector on the right-hand side is also going to be an element of Rm, and here we're going to assume that lambda is going to be a scalar that belongs to the scalar field, let's say the complex numbers. So if we take this and look at this perspective from the differential equation side of things, and we write, for example, the equation the derivative of y is equal to lambda y, where y is a differentiable function, then pretty much these equations are practically the same exact thing. So for example, the derivative operator we know is a homomorphism. So this is a homomorphism from, and we know a few vector spaces that we have worked on in the past. For example, Pm, the set of polynomials of degree n or less, so it's going to be a homomorphism from Pn to, for example, Pn minus 1, because it takes the degree and subtracts by 1. So this function y is going to be an eigenfunction for the derivative operator d over dx, and lambda, of course, as usual, will be our eigenvalue. So one can say, well, what is the eigenfunction for the differential operator d over dx? And we're going to look at this in particular today. Now, of course, Pn, the set of all polynomials, is not the largest class of differentiable functions. So what we're going to consider is the derivative operator d over dx to be a homomorphism from C infinity to C infinity, so it's going to be a larger class of differentiable functions. So let's just give a brief definition of C infinity, and some people will also write this as C infinity on the set of real numbers R. So this is going to be the set of all vectors u, or the set of differentiable functions u, such that the nth derivative with respect to x of u exists for all n on some domain, typically of R, right? And of course, if u is an element of C infinity, if you've taken single variable calculus, then this implies that u has a Taylor series, right? So one can prove, once we have this defined, is the following theorem. So theorem C infinity is a vector space. In particular, it's a vector space of infinite dimension. Now, we haven't really talked about infinite dimensional vector spaces a lot, at least so far in this linear algebra series, but there are different sizes of infinity. In particular, for this particular infinite dimensional vector space, one can show via some cleverness that the dimension of C infinity is going to be equal to 2 to the power of the cardinality of the size of real numbers. So call the number of real numbers, let's call that, for example, omega. There's going to be 2 to the power omega vectors that will serve as a basis for C infinity, which is quite a lot, right? So we're not going to attempt to list them all here. Right, so let's consider a subset of the set. So let's consider the set, which we're going to abbreviate as S subscript m, and it's going to be the set of all functions y in C infinity, such that the sum from k is equal to 0 to m of ak, and then the kth derivative of y is equal to 0, with a restriction on those coefficients, in particular the leading one, is equal to 1. So if we expand this expression what we have. So we're going to have the nth derivative of y plus some constant a n minus 1 times the nth minus 1th derivative of y plus, and that's going to go all the way down to, for example, a1 times the first derivative of y plus a0 times the 0th derivative of y, which is just equal to the original function, and that's going to be equal to 0. So we're going to be considering the set of all functions y and c infinity that are solutions to this differential equation. And this differential equation is very special. In particular, these numbers here are all going to be constants. So here a k belongs to the set of real numbers, or the complex numbers, that's okay. And notice that the right-hand side is equal to 0, so we don't have like equals to 5, equals to sine x, or equals to anything like that. And the highest derivative in this expression will be equal to m. So this is what we refer to as an nth order linear constant coefficient homogeneous, that's what the 0 at the end means, ordinary differential equation. So ordinary differential equation. So Sn is going to be the set of all solutions to nth order linear constant coefficient homogeneous ordinary differential equations. Right? So what is so special about this set? Well, one can show that Sn is a subspace of C infinity. So how would you go about proving that Sn is a subspace of C infinity? Well, first off, the 0 function belonging to C infinity belongs to this set Sn. So that's the first requirement to be a subspace. Also, if you let k be some scalar in the set of scalar fields that you have chosen, one can show that if y is an element of Sn, then ky will also be an element of Sn, and I'll leave for you to verify that that is the case. And thirdly, if y1 and y2 both belong to Sn, one should be able to show that the sum of y1 and y2 also is going to be in Sn, right? So it's closed in a scalar multiplication, it's closed in a vector addition, and the 0 vector belongs there. And since C infinity is a vector space, let's say by axiom, and these three properties satisfy, we have that Sn is a subspace of C infinity. Now that we have a couple of the building blocks discussed for this C infinity, in particular this subspace of differential equations, now let's see if we can try to build what the solutions of that vector space looks like. So let's just recall just a couple things from single variable calculus. In particular, the derivative of the exponential function is equal to e to the x. So this expression from differential calculus should reminisce from the expression ay is equal to y. So y equals to e to the x would be an eigenfunction for the differential operator d over dx with eigenvalue 1. But of course we can extend this just a little bit because we know that the derivative of e to the lambda x, where lambda is a scalar, is going to be equal to lambda e to the lambda x. And this equation should reminisce from the equation ay is equal to lambda y. Again, y equals e to the lambda x is a broader eigenvalue, eigenvector, or eigenfunction for the differential operator, and lambda its associated eigenvalue. So if we consider the first order linear constant coefficient homogeneous differential equation, y prime plus ay is equal to 0, and we choose, for example, this eigenfunction for this differential operator because we know eigenvectors form a basis for the vector space for which these homomorphisms serve over, then what will we get? Well, if that's the case, then e to the lambda x derivative plus a e to the lambda x is going to be equal to what? So that's going to be equal to lambda e to the lambda x plus a e to the lambda x, and that's going to be equal to 0. Well, if that is the case, because we're not really sure that e to the lambda x is going to be a solution because we don't know exactly what lambda is, well, this will be true if and only if lambda plus a times e to the lambda x is going to be equal to 0. Keep in mind, if lambda is a real number, this is never equal to 0, so we have that lambda must be equal to minus a. So if lambda is equal to minus a, then we have that e to the lambda x will be a solution to our differential equation. So if we have y prime plus ay is equal to 0, then y equals e to the minus ax is a solution. Now, is it the only solution to the differential equation? No, because if this is a vector in the basis, any scalar multiple of it also will be an element of the basis of the solutions for that vector space. In particular, we can say that y is equal to c e to the ax is the general solution to the differential equation, right? So any scalar multiples of that one basis function that we have found just by analyzing just eigenvectors of differential matrices. Now let's see if we can increase the order just up by 1. In particular, let's consider the second order differential equation, y double prime plus 4y prime minus 12y is equal to 0. So now our operator in this particular world is going to be equal to y double prime, or let's actually write it in differential form. So we have the second order differential operator minus 4 times the first order differential operator minus 12 of some function y is equal to something, right? So in this case, what we're looking for is we're looking for eigenvectors and eigenvalues of this particular differential operator, right? Which is a second order. So one may be able to guess, well, maybe this is going to be a two-dimensional subspace of C infinity. And one would be right. So we know that for the first order derivative operator, y equals e to the lambda x is an eigenfunction of it. So maybe we can just assume that both of them are going to be of this form, but maybe two different values of lambda. So let's see if that gives us anywhere. So what we're going to do is we're going to let y be equal to e to the lambda x be some ansatz solution because we know it serves as a basis for our one-dimensional subset of C infinity. So let's see if it's related to our two-dimensional subset. So if y is equal to e to the lambda x, then we're going to have, let's see, e to the lambda x, second derivative, minus 4 e to the lambda x, first derivative, minus 12 e to the lambda x, no derivative, is equal to 0. And that means that lambda squared e to the lambda x minus 4 lambda e to the lambda x minus 12 e to the lambda x must be equal to 0. We have an e to the lambda x for which we can factor out, and then we're just going to have lambda squared minus 4 lambda minus 12 times e to the lambda x is equal to 0. So as usual, we know that e to the lambda x cannot be equal to 0, so this is going to be true whenever this is equal to 0. So we know we can factor this as lambda minus 6 times lambda plus 2 is equal to 0. So we have two different values of lambda. Lambda 1 is equal to 6, and lambda 2 is going to be equal to minus 2. Right? And this equation here actually has a name in the realm of differential equations. This is referred to as the characteristic equation. And one can ask, was that any relationship to, for example, the characteristic equation for numerical matrices? And the answer is yes, but we're not going to be exploring that little thing, at least for now. So now that we have this, now we have two solutions. In particular, we have y is equal to c1 e to the 6x as our first solution, and then we have y is equal to c2 e to the minus 2x as our second solution. So these are our solutions to our ordinary differential equation. So one can say, well, what is the general solution? So the general solution will just be the linear combination of these. So that means the general solution, y, is going to be equal to c1 e to the 6x plus c2 e to the minus 2x. And that is indeed the general solution for our differential equation. So if that's the case, then one thing we need to verify is, are these vectors independent? So question, are the y solutions independent vectors of C infinity? Because if they're not independent vectors, then we don't have a basis of dimension 2. We just have a basis of dimension 1 or possibly less. So how do we prove that these vectors e to the minus 2x and e to the 6x are indeed independent? So if they are independent, then c1 e to the 6x plus c2 e to the minus 2x is equal to 0 if and only if c1 and c2 are both equal to 0. So we're trying to figure out, is it possible that we can do different constants, c1 and c2, that are both non-zero such that this actually equates to 0 for all powers of x? So we have one equation, but we have two unknowns. So how can we build another equation from this? So keep in mind, e to the 6x and e to the minus 2x both belong to c infinity, so I can take the derivative of them. And I'm going to keep these constants, c1 and c2, as they are, and I'm going to take the derivative of both sides of the equation, and that's going to give me a different equation. So when I do that, I'm going to have 6c1 e to the 6x minus 2c2 e to the minus 2x is also equal to 0. So once I have that, now I have two equations with my two unknowns. So let's actually write that out. So that means that c1 e to the 6x minus or plus c2 e to the minus 2x is equal to 0. And 6c1 e to the 6x minus 2c2 e to the minus 2x is going to be equal to 0. And I can write this in matrix form as e to the 6x, 6e to the 6x, e to the minus 2x, and minus 2e to the minus 2x times c1, c2 is equal to 0, 0. So what do we know about this particular equation? Well, we obviously know that 0, 0 is going to be a solution to this. And let's actually give this matrix a name. Let's call this matrix W. So we know that C1, C2, which is equal to 0, 0, is a unique solution to this differential equation if and only if the determinant of W, which is technically a function of x, is not equal to 0. So this matrix W is known as the Wronskian of the set e to the 6x and e to the minus 2x. And it's used to establish the independence or the lack thereof of the solutions in this set. So although this is just for two solutions, we can actually extend this to several more. So let's actually give the general definition of the Wronskian. So the Wronskian for the set S, which is equal to y1, y2, down to, say, ym, and let's assume that's the subspace of C infinity. So we can take the derivative of these functions as many times as we want, in particular n or n minus 1 times. So the Wronskian is going to be the matrix of the following derivatives. Let's scroll back down. So the Wronskian is going to be equal to the matrix y1, y1 prime, all the way down to the n minus 1th derivative of y1. And then we're going to have y2, the first derivative of y2, all the way down to the n minus 1th derivative of y2. And then we're going to go all the way down to ym, the first derivative of ym, all the way down to the n minus 1th derivative of ym. And one should be able to see that this is indeed an n by n matrix. And with this Wronskian, we can have the following theorem. So S is an independent set of solutions. Actually, let's not talk solutions. Let's just say vectors or functions of C infinity if the determinant of the Wronskian does not equal to 0 for all x either in R or on the domain of interest for which you're actually solving differential equations over. Right? So S is an independent set of vectors if and only if the determinant is not equal to 0 for all x. So let's look at our particular set of vectors that we built before. So e to the 6x, e to the minus 2x. Is this an independent set of vectors? So the determinant of the associated Wronskian is going to be equal to the determinant of the matrix e to the 6x, 6e to the 6x, e to the minus 2x, and minus 2e to the minus 2x, which is a 2 by 2 matrix, so we know some tricks for that. So it's going to be e to the 6x times minus 2e to the minus 2x, so that's going to be equal to minus 2e to the positive 4x, and then minus the product of the off-diagonal entries, so 6e to the 6x and e to the minus 2x, so that's going to be equal to minus 6e to the 4x. And we can simplify that. That's going to be equal to minus 8 e to the 4x. And what does minus 8 e to the 4x looks like? So that's going to be an exponential that's going to be going down, which is never going to be equal to 0 for all x. Right? So since that is the case, that means we have that S is an independent set of vectors of C infinity. So with that in mind, now we can say that the original general solution is, in particular, the solution to that differential equation for that space. And let's formally state that here. So let's give a theoretical perspective. So every solution of y double prime minus 4y prime minus 12y is equal to 0 can be written as a linear combination of S vectors. In particular, a set of vectors of at least dimension 2, because that creates a two-dimensional vector space, as we've already explored. All right. Now, we've only shown this for 2 vectors, but technically we can take that Wronskian and extend it with that general definition. But I'll give this as a theorem, and you can do mathematical induction on this if you want. So if all eigenvalues of the associated characteristic polynomial are unique, then the set S, which is equal to e to the lambda 1 x, e to the lambda 2x, all the way down to e to the lambda n x, will form a basis for the solution set of the associated differential equation, which is the principle that we have. So if we have an nth order differential equation like y to the power y sixth derivative or something like that, ideally, if our characteristic equation gives us 6 unique values, which we're going to be calling eigenvalues, even though we're not really looking at numerical matrices now, if we do the linear combination of those exponential functions, e to the lambda kx, that'll form the general solution for our ordinary differential equation, as long as they are unique. So one may ask, well, what if we have repeated eigenvalues for our characteristic equation like 2 and 2, or 3, 3 and 5, or all of them are equal to 10? What do you do there? Because then this theorem doesn't apply, and then we have to be a little bit more creative on how to build our general solution, or basis vectors for that vector space. Let's consider the following second order differential equation, y double prime minus 4y prime plus 4y equals 0. So let's assume that we don't know any new tricks and we just try to approach it as the same way as before. So let's assume we have y is equal to e to the lambda x as our proposed solution, because we know e to the lambda x is an eigenfunction for a differential operator, at least of first order. So if we substitute that and cancel out the exponential of e to the lambda x, we're going to have the characteristic equation lambda squared minus 4 lambda plus 4 is equal to 0. Which of course factors into lambda minus 2 times lambda minus 2 is equal to 0, or lambda minus 2 squared is equal to 0. So notice that we have a repeated eigenvalue, lambda 1 and lambda 2 are both equal to 0, or both equal to 2. So if we look at our set corresponding to that, for example, e to the 2x and something, that will form the basis for our general solution, but we can't put e to the 2x there because that's a dependent set. So what do you think this other solution, in question marks, is actually equal to? So let's assume that our second solution, y2, is of the form f of x is equal to or multiplied by e to the 2x. So it's a product of our first basis solution and some other function. That f of x could be sine, it could be cosine, it could be polynomial, we don't know. But if it is a solution, we should find some constraints on that function f and then be able to verify that it indeed works once we find it. So if we take this as our solution, let's find the first derivative of it. So the first derivative of this is by the product rule is going to be equal to the first times the derivative of the second plus the second times the derivative of the first. And if we take the second derivative of this function, we're going to have the first times the derivative of the second, so 4 f of x e to the 2x, plus the second times the derivative of the first, so 2f prime of x times e to the 2x, so that is the derivative of the first. And then we can do the same for the second. So 2e to the 2x, f prime of x, and then plus e to the 2x, f double prime of x. So that is the derivative of that term, right? So if that's the case, and we substitute that into our original equation, which keep in mind was y double prime minus 4y prime plus 4y is equal to 0. So if we substitute y double prime, 4y prime, 4y for our y2, y2 prime, and y2 double prime, we should get some equations in terms of f. So once we do that, we're going to have 4, I'm just going to write f instead of f of x, e to the 2x, plus 4f prime e to the 2x, plus f double prime e to the 2x. So that's our f double prime because I've just combined like terms for those middle two terms. And then minus 4 times 2f e to the 2x plus f prime e to the 2x plus 4f e to the 2x is equal to 0. So once I combine like terms, what am I going to have? So this is going to give me 4f e to the 2x minus, so notice I'm going to have minus 8 there. And I also have a plus 4 term there as well, so I'm going to have 8f e to the 2x. And then I'm going to have a plus 4 as well, so plus 4f e to the 2x. I'm going to group them together. And then I'm going to have, so let's look at our f double prime terms, or single prime. So I'm going to have 4f prime e to the 2x minus 4f prime e to the 2x, and then I'm going to have plus f double prime e to the 2x is equal to 0. So notice that that cancels as well, and we're just left with the equation f double prime of x times e to the 2x is equal to 0. And since e to the 2x cannot be equal to 0, we have the equation f double prime of x is equal to 0. So if you know anything about basic derivatives, you should know that the only functions that vanish when you take the second derivative are going to be linear functions. That is, we have that f of x must be equal to ax plus b. So that's our basic linear function, our mx plus b typical things. So our first solution from our theory of differential equations, so y1 was equal to e to the lambda x, and our second solution via that logic is going to be equal to ax plus b e to the lambda x. But if we distribute this e to the lambda x to each of those terms, we're going to have ax e to the lambda x plus b e to the lambda x. But we technically don't need this b e to the lambda x term because we already have an e to the lambda x terms, and both of these would be dependent on each other. So that's not really contributing anything to the story. So the main part that we can really grab out of this is going to be this x e to the lambda x term because that's a completely different function. So this x e to the x is the only part of interest. So it's the only part of interest. So if that's the case, our next question is this. Is s equal to e to the lambda x and x e to the lambda x an independent set of C infinity? So if we look at the Wronskian of that, so the determinant of the Wronskian for this particular set is going to be equal to e to the lambda x, lambda e to the lambda x, and then we're going to have x e to the lambda x and then a quick product rule, so lambda x e to the lambda x plus e to the lambda x. And we're going to be taking the determinant of this particular matrix and see what we get. So that's going to be equal to lambda x e to the lambda 2x, and then plus e to the lambda 2x. So let's write it as just 2 lambda x. So we take lambda x, so that's the product of that term and that term. Now let's subtract the product of those other two terms. So minus lambda x e to the 2 lambda x, and that's going to come out to what? So notice that that term and that term are the same, so we can cancel those out, and we're just going to be equal to e to the 2 lambda x. So we know that this is greater than or equal to 0. Actually, I'm not going to say it's greater than or equal to because our lambda could be negative, but it's not going to be equal to 0 for all values of x, right? So that means that the set S is an independent set of C infinity. So let's conclude for our example and what we can say. So that means for our differential equation, y double prime minus 4y prime plus 4y is equal to 0. The general solution is going to be equal to y is equal to c1 e to the 2x plus c2x e to the 2x, where c1 and c2 are scalars, but that is going to be our general solution. Right? So that's what you can do when you have repeated scalars in your characteristic equation. Just a quick review before we move on to one of the last points I want to bring up. Consider this differential equation, y double prime plus 4y is equal to 0. Notice that we do not have a first order derivative term in this linear constant coefficient homogeneous differential equation, so it may be a little bit more easier to solve. So if we use our ansatz solution, y is equal to e to the lambda x, and then simplify that to get our characteristic equation, we're just going to have lambda squared plus 4 is equal to 0, for which we can easily solve for eigenvalues plus or minus 2i. So we have two different eigenvalues, so our solutions, y1 and y2, should be very easy to state. In particular, it should be equal to e to the 2ix and e to the minus 2ix. And that's it. And you can use linear combinations of those two. Now, although this is perfectly fine, it's not very useful, at least in terms of practice. So remember that e to the I theta is going to be equal to cosine of theta plus I sine of theta. So that's Euler's equation that relates complex exponentials to just the sine and cosine. And if you remember the even and odd properties of cosine and sine, then you can do or represent these in very nice ways. In particular, e to the 2ix is just going to be equal to cosine of 2x plus I sine 2x, and this is going to be equal to cosine 2x minus I sine 2x. So, just as before, the general solution is going to be linear combinations of these two functions. So that means y is going to be equal to c1 cosine 2x plus I sine 2x, and then plus c2 cosine 2x minus I sine 2x. And then we can distribute those constants and regroup. So we're going to have c1 plus c2 cosine of 2x, and then plus I c1 minus c2 sine 2x. So this is just a constant in c, and this is another constant in c. So for example, we can call this gamma 1 and gamma 2. So therefore our solution, y is going to be equal to gamma 1 cosine of 2x plus gamma 2 sine 2x, and that's going to be our general solution, where these constants, gamma 1 and gamma 2, are now in the scalar field of C. Or you can decompose the gamma 2 and just write that as gamma 2 times I, and then gamma 1 and gamma 2 will be real scalars. But keep in mind, for the differential equation, the solution doesn't really look like exponentials, it rather looks like combinations of sine and cosine waves, just split across the complex plane. Up to this point, you should be able to solve any nth order constant coefficient homogeneous differential equations, provided that you can find those lambda values that satisfy that associated polynomial characteristic equation. But instead of finding the general solution, let's assume we're looking for a particular solution that satisfies some criteria. So for second order differential equations, in order to find those C1 and C2 constants, you need two conditions. So most of the time, we assume that those conditions are associated to the same domain point. The first thing you want to specify is where do you want your solution to pass through, what point, and for that same exact domain value, what value do you want your first derivative to pass through. So if it was a third order differential equation, you would specify, for example, y double prime 0 is equal to something, and for example, order equals number of initial conditions, that's what these are called, is needed to give a specific solution. So with that in mind, let's assume that we're just looking for our general solution, and then we can find those associated constants, C1 and C2, and find a particular solution from there. So as usual, we're going to assume that e to the lambda x is going to be our particular eigenfunction for this differential operator, which we have already verified it is. So if we substitute, we're going to have lambda squared minus 5 lambda, and let's assume this is minus 14, is equal to 0, which we can factor as lambda minus 7 and lambda plus 2 is equal to 0. So we have two values, lambda 1 is equal to 7, and lambda 2 is equal to minus 2. Should be lambda, not y. So once we have our particular lambda values, we can state our general solution. So our general solution is going to be y is equal to c1 e to the 7x plus c2 e to the minus 2x. So now we want to use those initial conditions to find out what these constants c1 and c2 are. So remember, we have y0 is equal to 5 and y prime of 0 is equal to 1. So if we use our first initial condition, y0 is equal to 5, that's going to be equal to what? So we're going to have 5 is equal to c1 e to the 0, which is 1, which is nice, and then plus c2 e to the 0, which is also just c2. So every time you have exponential solutions, having 0 as your initial condition number always makes stuff nice. So now let's look at our derivative. So we're going to have 1 is equal to, so that's going to be equal to 7c1 minus 2c2. So we need to solve this equation for c1 and c2. So we can write this in matrix form as just 1, 1, 7 minus 2 times c1, c2 is equal to 5, 1. So 5, 1. So this is just our Wronskian evaluated at 0. So what is the determinant of the Wronskian evaluated at 0? Because hopefully it just gives us a unique solution. So the determinant of the Wronskian evaluated at 0 is just going to be equal to 1 times minus 2 times 1 times 7. So minus 2 minus 7, which is going to be equal to minus 9, not equal to 0. Therefore, we're going to have a unique solution. Now, what we're going to do is we're going to do Cramer's rule to solve this equation, although you could probably solve this in many other ways. So let's do the determinant of our W1 evaluated as 0. So this is going to be a partition Wronskian, I guess you could say. So this is going to be equal to the determinant of, so we're going to be replacing column 1 with our solution column. So it's going to be equal to 5, 1, 1 minus 2. So minus 10 minus 1, which is going to be equal to minus 11. And the determinant of W2, 0. So that's going to be equal to the determinant of 1, 7, and then 5, 1. So it's going to be equal to 1 minus 35, which is going to be equal to minus 36. And in case you're not familiar with this method, this is referred to as part of, at least, Cramer's rule. So from these three pieces of information, we can find that our constant, C1, is going to be equal to minus 11 divided by minus 9, or just 11 over 9. And C2 is going to be equal to minus 36 over minus 9, or what is that going to be? 1 minus 35, that's 34, by the way. That's 34. And that's going to be equal to 34 over 9. So once you have your constants, then we have our particular solution. So our particular solution is going to be as follows. So y is equal to 11 ninths e to the 7x plus 34 ninths e to the minus 2x. Right? And that's how you can solve initial value problems of any order, provided that this is a homogeneous, linear, constant coefficient, homogeneous differential equation. Now, of course, differential equations can be extremely more complicated when you, for example, break the inhomogeneous case, or the nonlinear case, or the non-constant coefficient case, but we'll save that for a differential equations lecture. But until then, take care.